This is jacket sizes. So this is really all about, there's two ways to do this. This is either find the pattern, because they keep going all the way and then they get to 48 and then they have a question mark down here because there's, what is the pattern here? There's one way to do it. Whenever I add 2 to this, I add about 5 to this, right? And I don't think it's not perfectly 5, but that certainly is close enough. Another way, anybody do this a different way? Because here the next blah blah blah, then you got 46 was 117. So now that we know the pattern, 48 should be, what was the pattern again? You just keep, yeah, it should be 122. Every time you add 2 here, you should add 5 there.
I did it a different way. I thought it was taking the bottom and dividing it over.
Sure, that's the other way to do this, is to divide these two. Because what is 86.5 divided by 34? Somebody help me out. Should be about 2.54. Because they rounded these numbers, that's why. But it comes out close to 2.5 something, right? Every single one of these, when you divide, you should get something close to 2.54. So how do you get for 48 then? You multiply it by 2.54, and what do you get when you multiply? What's 48 times 2.54?
48 what?
48 times 2.54.
1.1.92.
And that rounds to 122. So they rounded these numbers here. So again, if you like this, and personally I like this too, they keep adding 2, and what do they keep doing down here? Adding 5, roughly. It's not a perfect adding 5, is it? Because they rounded. But it's close enough to get a decent, estimate, right? Or you see what these, they always are multiplied by the same thing. And does anybody have a clue what that 2.54 is?
Centimeter.
I love it. Every inch has 2.54 centimeters in it. These are inches, these are centimeters. That's really all there is to it. Every inch has 2.54 centimeters in it. So that's really the conversion there. But if you saw the pattern, that's excellent too. That's beautiful. I love it. Because what's 5 divided by 2? 2.5, right? So they're really the same thing, just rounding on one of them a little bit. But that's the problem all about seeing the pattern. And there are 2 main ways, adding or multiplying. Both patterns give you the same answer at the end. It's all about looking for the pattern. Okay. So some of you guys are going to love this stuff, and some of you guys are going to totally hate it. But it's a little, the nice thing from algebra is you're freer here. Because algebra is just one thing you could use. You're free to do whatever comes to your mind as long as you kind of let me in on your thinking. Make sure I know what you're doing. Right? Okay, all right.
I have another quick question.
Yeah.
For number 40, where it says the cube, what happens if the cubes were all doubled? What happens? Is it?
So do this here. So if it was 111, what's the volume? 1. If I doubled all the sides, what would it be? 2, 2, 2. What's the volume? 8. So the volume here is 1. The volume here is 8. The volume becomes 8 times bigger, right? Because cubes are cubed. So if I double a side, every side length, 2 cubed is 8. The overall thing gets 8 times as big. Cool? And that actually leads to, like, if you see in the paper, they say, here's the taxes from 19 whatever, and then here's the taxes today. They've doubled the taxes, and they have this picture of a cube. They're misleading you. This is 8 times as big. So you go, holy shit, look at that big pot of money they got. And they're misleading. That's not allowed. That's not legal, right? Because they're actually making it 8 times as big. They're overstating the thing. And they use that all the time. They love having 3-dimensional pictures to demonstrate something. That's misleading you. right? Because the actual change is 8 times as big now, right? 8 times the volume. Okay. Anything else from?
Is that because you're adding a third dimension? Because you're adding a third dimension.
Well, yeah, actually adding 2 dimensions, truly. Straight line gets doubled. An area would get 4 times as big, because it would be 2 times 2. And the volume would get 8 times as big, because that's 2 cubed. 2 times 2 times 2. Yeah.
I was having trouble with 52. The one?
Oh, 3, 1?
Yeah. 1, 3.
1, 3.
Yeah, the one that was
50.
the magic cubit.
Oh, magic square.
Magic square.
Yeah. Wait, this is from earlier. They give you, I think, an example magic square, don't you, don't they? Yeah. Notice, look at page 29. They have these numbers, and they want to put those numbers, come on, Jeff, in here so that they get the same sum if they go across, down, or diagonally, right? Diagonally too? Yeah. They want the same sum, right? And the trick is, what should go in the middle?
The middle number.
The middle number should go in the middle, right?
But I don't think that's 29.
Oh, this is example 7, page 29. Because I know the numbers they gave you on the problem were different, but the process is the same. So if I put 5 here, so now notice this, what's 1 plus 5 plus 9? What's 2 plus 5 plus 8? It's got to be 15. Because if I make one number go up and another number go down, it's the same stupid sum, right? That's the idea. So 15 is the sum that can repeat because you can make 15 in a lot of different ways. So one way to do it is like that. That's 15, right? Now, you got to be a little careful. Do I want to put a 2 here? Because 2, 1, that's never going to make 15, right? So you got to be a little careful. So if I put 2 over here, then 8 would have to go here, right? 2, 5, 8. Then what has to go here to make 15 here? 6. What has to go here to make 15 here? 7. Right? What has to go here? So it's 11, 11, thank God. See, 4. And then what's the only number left? 3. And does it make 15? Yes. So they actually give you, so they give you different numbers. It's the same process though, right? So the numbers they give you on number 52 are 1, 3, 5, 7. That's the one we're doing, right? 52? 1, 3, 5, 9, 11, 13, 15, 17. What's the middle number? 9. So that's got to go in the middle. So what's the extreme here? 1 and 17, right? So now you know what the sum is you want to have. 27, right? So now build it the same way we built that one. Build it the same way. You don't want to put 3 here, do you? Because then 3 and 1 is too small. I can't make 27 that way, right? So put the 3 over there. So what's got to go there? So what's got to go there? So what's got to go there? So I've almost got that one done for you now. That's the idea of those, right?
I'm seeing a pattern. For example, you put the 9 in the middle. If you take the 1 and the 17, they have to go beside the 1 and the 17. And then the next numbers are 3 and 15. They have to go diagonally. And then the 3 and the 13, excuse me, have to go on the other diagonal.
Good. So some of you guys might realize you can actually turn this around. You don't have to put the 1 and 17 there. There's several ways to kind of put those on the outside. Kind of like turn it like a clock, but this is a good kind of way to attack it. So, sure, if you see the pattern, great. If you don't, at least you have a way to start. Middle number in the middle, extremes out there. I can't put the 3 there, so maybe I can put it there. Could I put the 3 there? Sure, why not? As long as it's not in this row, because the 1 is too small. 1 and 3 is 4. Do I have a 23 I can work with to make 27? No. So So I don't want to put the 3 with the 1, right? So I really don't want that to be a problem where you can rip your hair out. If you don't start with that 9 in the middle, it ain't going to work. So you can really start to go crazy if you try to just start putting all stuff anywhere. Get that 9 in the middle, extremes around it, and then you can go from there. You should be able to build it up from there.
But you can always do it differently, right?
Sure, there's other ways. That's the way I thought about it. How did you do it?
I took the highest numbers and made a diagonal.
So you took, now, so what did you do then? You took the highest numbers?
Yeah, like 13, 15, and 17, and I did them diagonal.
Now the problem with that though,
So the highest numbers don't go together.
yeah, but this adds up to be what?
Oh.
It has to add up to the same number if you go across, down, or diagonal. That's the thing, you gotta be careful with.
Yeah.
That's why the middle number has got to be the middle number, right? Because it then can handle it when this goes up, if this goes down, it's the same number in the middle, it's all balanced again, right? That's the idea. Number 1? Oh yeah.
Oh no, never mind. No, number 3.
3.
3.
So if a 3-foot stick in the ground casts a shadow
Yeah, number 3.
of 1.2 foot. And this is the whole idea behind how do you measure the size of a tree. There's actually several ways to do it geometrically, but one way is to measure the shadow at a certain time of day. And then compare it to something you can actually get to the top of easy. I don't want to climb to the top of the tree and bring a tape measure up with me. Right? Some of you guys might know surveying, and you might know about using angles. But in other words, just look at the shadow. So if a 3-foot stick, so I can handle a 3-foot stick, and I measure its shadow. And then I've got a, well, just kind of backwards, but find the length of the shadow if I have a 48.4 foot tree. How long would its shadow be? What could you do?
Is that a 3 over 1 point?
I love it. This is a proportion problem, right? What's this?
X.
X. There's another situation where algebra might help out a little bit. You could do this without algebra, so if you did it without using a variable, you're fine. But now you can say a 3-foot object has a 1.2 foot shadow. So a 48.4 foot object better have a I don't know yet shadow, right? Because the proportion's got to be the same. Right, 3-foot stick casts 1.2, so a 6-foot person better cast a 2.4 foot shadow. That only makes sense. So extend the idea to a big old 48.4 foot tree. Now how do you solve a proportion? The only time you're allowed to cross multiply is 1 fraction equals 1 fraction. People try to cross multiply too often. So you can finish that out, right? Not a big deal. Anybody do it differently? You can even set up the proportion the other way. As long as it's real to shadow, real to shadow. Or you can do shadow to real, shadow to real. It's got to be set up the same ratio, right? To make this work.
How would you do it if you weren't using fractions?
You would see what the multiple is. 3 divided by 1.2, see what the multiple is, and then divide that by the same thing. So it's the same math, you're just not explicitly bringing algebra into it. You don't have to bring an x into it necessarily. Right? Okay. So anything else from 1 to 3? Okay. So we're going to get back into logic. And going back to section 3.1, let's do a few problems out of the homework so we see what this is going to look like. So let's take a second, actually remind me now,